Let's pick up where we were from the last video. We had this system of equations where we had a plus b equals 3 and 2a minus 3b equals -1. Well, in systems of equations, one technique that we can use to solve them is to put one variable in terms of the other, and then take that information and plug it into the other function that is in your system. So everywhere I see a, I can write 3 minus b. So that's all I'm doing here. Where I see a, I'm substituting in 3 minus b. And now I have an equation completely and totally in b. So this gives me 6 minus 2b minus 3b equals -1. I can add like terms and subtract 6 from both sides, and that tells me b has to be 7/5. Now I can come back up to this equation, and I can plug that b value in there, and I can solve for my other variable. This must also be a true statement. So a should equal 15/5 minus 7/5. So a is 8/5. Now we have completely rewritten our original rational expression in terms of two fractions. Now it's important that you have that for reference so that you know the value of a is paired with the denominator of x minus 3. So this is equivalently written as 8/5 times the quantity 1 over x minus 3 plus 7/5 times the quantity 1 over x plus 2. And we're guaranteed that this is equivalent to the original rational expression we started out with. And the beauty of it is, look here, if we are inside of an integral, we go from an integrand that we don't stand any prayer of being able to find the antiderivative of to two separate integrals that are u substitutions that we can definitely find the antiderivative for. Here, this is a u substitution where u is x plus 2, so du is dx. This is equivalent to 7/5 times the integral of 1 over u du, which is 7/5 times the natural log of u plus c. So this term would simply be 7/5 times the natural log of the absolute value of x plus 2. Over here, equivalently, another u substitution, a very simple, straightforward u substitution. And the antiderivative here is 8/5 times the natural log of u plus c. So we would simply add that term here, back substituting into the original variable, and there is our antiderivative function. So not only can we find it, but it's fairly easy to find. So there's the power. There's an illustration of the power of partial fraction decomposition. We have one more quick example that we'll go through. It turns out that you see this on the multiple choice part of the exam quite often, and I consider it free and easy points because it's not a difficult process. You just have to be meticulous with your algebra. So again, you must write this for yourself as a reference, all right? Because you're going to come down here and you're going to find a equals this value and b equals this value. And by the time you get down there, you're going to have forgotten which numerator you had which letter attached to. Plus, someone over here may write their two separate fractions completely different than you did. And in this case, what this person gets as a value of a, that person got for their value of b. All right? So you have to make sure you give yourself a reference to go back to. And all of this must equal 3 over the quantity x minus 1 times the quantity x plus 2. So we're multiplying by well-chosen ones. This fraction gets multiplied by a fraction that's x plus 2 over x plus 2. I'm only going to write down what's happening in the numerator because the denominator, I'll just show you here, the denominator for all of the terms when we're said and done is going to be the same. So usually what you'll do is you'll just drop that whole denominator work and you'll concentrate on what's happening only in the numerator. So this fraction gets multiplied by a well-chosen 1 that is x minus 1 over x minus 1. And then that result has to be 3. So usually what you'll see is you'll only see the numerator portion of things because all the denominators are the same, right? So we really just worry about what's going on in the numerators there. And I'm fine with that. That's all the AP reader is going to want to see anyway. So here we are. Let's try that again. And that has to equal 3. So I'm going to show you an alternate way, not necessarily better, just different, of coming up with A and B where you can bypass the systems of equations work. Here, if you'll realize that if you can choose a value of x that forces this entire term to go to 0, then when you plug that value of x into every single term on both sides of the equal sign, then it's going to be much easier to solve just for one variable because you've forced one of your variables to go to 0. So if I plug in x equal negative 2 into all three terms here, then the result is 0 plus b times negative 2 minus 1, which is negative 3. And now I just have one equation with one variable. And that equation is negative 3b has to equal 3. So very simply, we found out that b equals negative 1. And now we can come up with another value for x and plug it into every term. That forces this term to have a value of 0. So I wind up with a times 1 plus 2, which is 3, plus 0 equals 3. And a has to equal 1, while b is negative 1. And again, I have to remember which denominator was attached to which letter, A and B. So now we'll come down here, and I equivalently have the integral of 1 over x minus 1 plus a negative or minus a 1 over x plus 2 with respect to x, and we're integrating from 2 up to 3. So our antiderivative is the natural log of the absolute value of x minus 1 minus the natural log of the absolute value of x plus 2, and we're going to apply fundamental theorem. So what we have here is the natural log of 3 minus 1 minus the natural log of 3 plus 2, there's my upper limit, minus the natural log of 2 minus 1 minus the natural log of 2 plus 2. So again, if this was a free response question, that's a real number value and I could just walk away from it. But on multiple choice, I'm going to have to clean it up. And if my answer has a natural log in it, it's written as a single expression in the logarithm. So this is one context where those properties of the natural log are going to be used, where it's really important. So this is the natural log of 2 minus the natural log of 5. Let's see, minus the natural log of 1, and this is a minus minus, so plus the natural log of 4. That term goes to 0, and notice all the rest of my expressions are positive. So at this point, it's fairly easy for me just to drop the absolute values. I could clean it up a little bit. Now remember, if we have positive terms, then when we add logarithms, that result is a single logarithm where we multiply their expressions. So the natural log of 2 plus the natural log of 4 is equivalent to the natural log of 8. So what I have now is equivalent to the natural log of 8 minus the natural log of 5. And there's that logarithmic property that says if I'm subtracting logarithms, then it is the expression of the positive logarithm over the expression of the negative logarithm. And so natural log of 8/5, which is here, is choice D. So lots of algebra, lots of pre-calculus going on here to actually find that final answer. But the things that I want you to remember about this process are that you absolutely need to write this down as a reference for yourself to refer back to, so that when you find your values for A and B and plug them into your integral, that you get the right numerator with the correct denominator linear factor. So that completes this partial fraction decomposition lesson. Come to class next time and we'll work some homework problems.